Hello, welcome to another problem session. Well, we are working on rotation these days, but we skipped over earlier in our discussion couple of weeks back when we discussed momentum, the concept of center of mass. And it's going to be important for our rotation discussions. So I want to go back and fill in the concept. You have to be clear on this. You have to be clear on the center of mass idea. So center of mass is a measure of how mass is distributed in a system. So if you have two masses. And so you have two masses m and they're equal distance, then there is a point right in the middle that will be the center of mass point, that from the symmetry. So we say that in every direction you go from here, you find the same amount of mass on both sides of this point. That's what it means, find the same both sides. So if you have a rod which has uniform density, it's like say iron rod, then the center of mass will be right in the center, or the mass is distributed evenly on both sides. So if you have a sphere, for instance, the center of mass is right in the middle. Now if you have a sphere and you have a cavity here, so you have mass all cavity here, so your center of mass will not be at the center but a little bit on the left side. Center of mass will be there. So, but you have to find out exactly where the center of mass will be. If you have a cylinder, then center of mass will be again at the center. So if there's uniform, it's this symmetrically placed point. And there's a definition, from the definition of center of mass, we should be able to calculate the location of center of mass. So what's the definition of center of mass? Definition is, so I'm going to do a mathematical definition. And so here is some body object whose center of mass we want to know. So we can break up this object into little cells. So each cell has a cell ith cell. It's located at Ri vector from this O. So this is this is the xi, yi, zi of the cell. Another way to say the vector. And in that cell, say, has mass mi. Okay, so we can just call it delta mi for a small amount of mass, if you like. Then if you add up all of this, so amount of mass, we just omit this for now, amount of mass times this vector. So this can be some mass, right? So mass times a distance unit, right? And this I equals go over all the cells. There are n cells. Now, center of mass will be, say, over here for this body, if this is the r center of mass vector, then center of mass will be as if the entire mass m was placed at that point. So this would be equal to entire mass. This whole thing will be equal to entire mass placed at r center of mass. So that defines the location of center of mass. Okay. So RCM you can write down as 1 over m total mass, sum over I equals 1 to n mi ri vector. And of course, if your RCM can be written in terms of x, y, z coordinates, and you can separate them out in x, y, and z coordinates. So like XCM is equal to 1 over mass and I equals 1 to n mi xi. So I only need xi's of these objects to find out XCM. And YCM is just 1 over m I equals 1 to n mi yi. And ZCM will be similarly, okay? So that is the definition of this. But if the object is continuous like that, in each cell will be, so for continuous object, each cell I has volume dxi, dyi, dzi. Say the density is rho, say kilogram per meter cube, and this is meter cube, right? So so mi mass in cell I is actually a differential element, rho dxi, dyi, dzi. So this sum that I'm summing over is actually becomes an integral. So RCM just becomes 1 over total mass mi rho dxi, dyi, dzi. So instead of dxi, dyi, we can just write down same amount of volume for each one of the. So we don't distinguish between the cells. Instead, we integrate over the entire range over which this density is. In an odd shape, it's going to be hard to put these limits, but in so it will be for all x, y, z in the body. So I'm going to integrate over this where x, y, z points are in the body. This times r instead of x ri. I'm not integrating I. So this is in cell, and this is the volume of the cell, and broken up into differential elements, so don't have distinction between different i's, and integrate. So this is the CM for a continuous body. Okay, let's see some examples of application of this formula. So let's look at an example. A very simple example will be a rod. So where is the CM? So rod has just thin rod of length L, And we already very easy to say Cm will be over here in the center at L/2. But we want to use this formula to see it. So the rod is very easy to write down. Let's see, want to find out where it is, okay? Suppose I don't know where is the Cm. So we'll work out the formula in x direction, and there's no y or z. So no y or z. So this formula will just becomes xcm equals to 1 over total mass, x in rod, and rho of the rod dx. That's it. And this rho will be kilogram per meter, because this is meter. So it's not kilogram per meter cube, per meter. Okay. And what is m? Rho x dx, because x will come from here. What is total mass is just rho dx, x in rod. So you can see that m is that, and so if I put the m in there, this will be rho L, because 0 to L, this integration will be 0 to L, just give me rho L. So 1 over rho L, and the rho comes out, and x in rod is going to be 0 to L x dx, and you can see this integration very easy to do, and rho cancel out, 1 over L, and this is half L squared, so this is half L. So that's where the Cm will be. So this is from here to here, this is half L/2. And you can do different shapes. Let's look at another example. So this is example 1, example 2. Let's see if I have a triangle shape, and this is the base and this is the height. And where is the Cm? It's pretty hard to tell now, so we are going to have to set up a formula, coordinate system, and look at what we can get. So this line, on this line is y is a function of x, is h over b x. So that's now we want to figure out along the x. So over here is the center of mass. What is this center of mass? That's what I'm going to figure out. Well, so our strategy will be pretty similar to that. We'll take a strip here, and in that strip we're going to find out how much mass to place along the x-axis. Different strip are going to be different. So all the way here we're going to have different amount of masses. So this is between at x and x plus dx. So how much mass should I place there? All the masses here. So all the masses will be dx here, and over here will be y. So this is area will be y times dx, and y is h over b x dx, right? So when we do this, if the density is rho kilogram over meter square now, so when I multiply this two, I'll get the mass to put in here. Amount of mass I'm going to put in, I'm going to just use the letter dm to denote the amount of mass to put in there. Amount of mass to put in there will be this product of the rho h over b x dx. Okay, so this is the amount of mass, and this is the amount of mass put in. So this is the dm. So xcm will turn out to be 1 over the total mass that's in this triangle, and along the x-axis I'm going to do x equals 0 to b and amount of mass. So this will be just one line, just like over here. It's just along the x-axis I'm doing, and I've got rho h over b x dx times x. So this whole thing, and so I get rho h over b over m 0 to b x squared dx. And what is m? M is just rho half times base times height. So we've got a rho cancelled out, got 2, h cancelled out, and I got 2 over b square, and this is b cubed over 3. So I've got 2/3 b. So from the tip, x is 2/3. So this is 2/3 b. That's the center of mass x is. And I don't need to do the y because it's going to work out the same way. From this tip to this will be 2/3 h. Y center mass will be there. So what we found is from this tip to that is 2/3 of this distance, and from this tip to that is 2/3 of that distance, and that's where the center of mass is. Okay, let me do one more, and that will be so let's do another example of a cone, example of a CM of a circular cone. So let me place the cone like this, just like I placed the triangle. Let this be x-axis from the center. So we can make use of this is y and this is z, right-handed coordinate system. So this part is h, and if you look at over there, that is r. So the radius is, this is r. Okay, so from the symmetry, we know it's going to be on the x-axis from symmetry. We can say YCM is 0 and ZCM is 0. Okay, so all I have to find is XCM. And so we could do exactly the same trick, but this time we take this strip at x, and all the mass we place right in that strip. So this will be the dm. So whatever the mass is in the dx, we place right there. How much mass is there? That we'll call it dm, and that's going to be rho and the volume times volume of this thing. So this is kilogram per meter cube now. So rho, the volume will be pi, let's call that y, okay, pi y square dx. Okay, so that's the volume of that little tiny thing. So the total mass will be, if you want to write the total mass, will be simply integral x, which goes from 0 to h now, 0 to h, rho pi y squared dy dx. But y, if you look at this line, this y is y to x. If you look at these two triangles, similar triangles, So the equation of the line on this y is r over height times x. That's the equation of this line. So that's this y is related to this x in that way. So this will be rho pi 0 to h r square over h square x square dx, and this is rho pi r square over h square h cube over 3. So rho pi r square h over 3. So that's the mass. And xcm will be 1 over mass times this whole thing times the x coordinate. So x times rho pi y square dx. So this is 3 over rho pi r square h for 1 over m, and this rho pi, and the y square again gets r square over h square, and this x square becomes x cube, 0 to h x cube over dx. So you work it out, and r square went away, rho pi went away, and this is 3 over h cube, and this one is h to the power 4 over 3 over 4. So this is 3 over 4 h. So we found it. We found that the center of mass is 3/4 from this tip, or 1/4 above the base. That's where the center of mass of a regular cone is. Okay, so you can see this calculation is pretty accessible. From this, most cases we'll deal with is going to be like this, or some centers. So we will do more calculations like this, when we do moment of inertia. And that is where we are headed next. Okay, so I'm going to stop here. Don't forget to subscribe to this channel, and it helps distributing this channel to wider audience. And if you hit a like button, then it also helps with the distribution. I'll talk to you later. Bye.